Hey everybody, thanks for tuning in. I'm Zach Peterson. I'm a technical consultant with Altium, and today we're going to talk about differential pairs. What are differential pairs? It's actually a really simple idea. It's two traces being used to carry a signal instead of one trace. That's the easiest way to explain it. Now, how they actually work takes a little bit more of an involved explanation. So we're going to get into that right now. Let's get started. What I want to talk about now is basically how signals are carried by differential pairs and what they look like in a PCB layout. And I'll actually show an image from a PCB layout that we've done that shows how differential pairs are routed. So differential pairs are really simple. It's two traces routed side by side. So I have my trace number 1 here and I have trace number 2 here. And differential pairs are put into a PCB to have a very specific width, W, and spacing, S. And there's actually a third parameter that you need. The third parameter that you need to define in your PCB, so I'm going to show the side view here, is a distance, H, above the ground plane. So here's my height above some ground plane, and I've got ground down here. Here's my side view with my traces. Here's my top view with my two traces right next to each other. So the two of these together, routed side by side like this in parallel, forms a differential pair. So this spacing is a little bit exaggerated. The width can be different depending on the height, but these parameters all taken together will determine the impedance of this differential pair. The individual trace on its own has its own impedance. And that characteristic impedance is just Z sub 0. This is normally the symbol that you'll see in equations used to describe the impedance of just an individual trace. The two of these together, based on the spacing between them and the size of the traces, will then have a differential impedance, Z sub D. There aren't really any good formulas that you can use or that you can really derive from first principles to get an equation for Z sub D. However, there are a lot of different calculator applications out there that can pretty reasonably determine this to some level of accuracy. If you're in something like Altium Designer, it'll have a field solver built into the layer stack manager that you can use to calculate this directly. Z sub D is the impedance that the signal sees when it's traveling along these two traces. So now the question is, how do these two traces carry a signal? So this is, I think, something that can get a bit confusing, but it actually relates to the same idea that's used to measure a signal just between one of the traces. So I'm going to redraw some of this and we'll look at how exactly the signal gets read out by a receiving component. So now what we want to look at is how exactly does this pair of traces carry a signal, and then how is that signal actually read out by the component that connects these two traces? So if you look at the signal that's carried by a differential pair, the signals are equal and opposite. So what I mean by that is if I draw out a graph of the signal for the top pair, it might look something like this. Obviously this is, squared off like this and it doesn't really look like that, but this just kind of gives you an idea. So this would be for the top pair. And maybe this is, just to keep it real simple, I'll say it's 1 volt. The bottom pair has an equal and opposite signal that it carries. So if this is a graph of the signal, it's actually not like this, it's negative of that. So here I need to draw my axis down, and here this level would be opposite sign of this voltage here, so it'd be -1 volt. Essentially this top trace is carrying this signal, this bottom trace is carrying this signal. If you were to take a voltmeter, again, not literally take a voltmeter, but if you were to measure the voltage between the trace and wherever ground is defined for this voltage, you would measure 1 volt. Similarly, if I were to take a meter or some sort of instrument and measure the voltage between this trace and ground, I would get -1 volt. So what the component that receives these two signals is doing is it's actually measuring out the difference between these two traces. So you can think of it as measuring the difference between this trace and ground, subtracting this trace and ground. So here I've got a ground potential at 0 volts. Here I've also got a ground potential, GND, defined at 0 volts. And if I'm taking the voltage between these two traces, then the voltage that I read out is just 1 minus whatever my ground potential is, minus -1 minus whatever my ground potential is. And so if I distribute the negative sign in, I combine like terms, and I subtract these grounds, these two grounds are going to cancel out, and then I would get 1 minus -1. So the voltage that I read out is just 2 volts. Here, this actually reveals something really important about differential pairs, and the reason that they have been used, and the reason that they're actually used on very long connections. Here, you'll notice that whatever my ground potential is here for this trace, and whatever it is here for this trace, doesn't matter. So this difference between 1 volt and ground and 1 volt and ground, it doesn't matter. So the ground potential totally cancels out. Essentially what that means is that the signal that's being carried by these two traces is immune to any fluctuations in the potential, as long as that potential affects both pairs in the exact same way. So this allows differential pairs to remove a certain type of noise called common mode noise. And this is one of the big advantages of using differential pairs, and it's actually one of the reasons that they're used in high-speed signaling. It's because they're immune to this very specific type of noise. So let's just say for a moment that there's a changing magnetic field, B dot, coming in this way, and the magnetic field induces a signal in both traces. Well, let's say it's a noise pulse. It looks something like this. And that identical pulse gets instituted over here on this signal. So here I've got a little bit of a noise signal, V sub n, and I have that same noise signal here, V sub n. So here, if I write out what the equation is for the voltage that I read out from these two signals, then what I'd have is, first I'd have my readout voltage is 1 volt plus whatever the noise voltage is, minus my ground potential, minus -1 volt, so that's this level here, plus the noise voltage, minus the ground potential. And so again, I've got positive noise voltage, negative noise voltage, so those cancel. Negative ground, and then minus a negative ground, so that's positive ground. Those cancel. And so again, I'm back to V sub r equals 2 volts. That's just coming from I have 1 minus -1. I get back to 2 volts. These other terms all cancel out and they're gone. And so I'm able to read out just the difference between these two levels because they're equal and opposite. So this is really important because there are actually two different types of noise that can appear in PCBs. There's common mode noise and then there's differential noise. Now, common mode noise is really important in differential pairs because, again, you can cancel it, and it's actually the type of noise that you would expect to see when you have some other trace elsewhere on the board that creates a very large changing magnetic field. And that would then induce some noise in both of these traces simultaneously. And that's the noise that you want to cancel out, because that's the noise that typically appears as crosstalk from some other part of the system. So when I say some other part of the system, that could be some other digital protocol that's running with a single-ended trace, which would then produce this type of changing magnetic field if it then switches very quickly, so if it's running at high speeds. Another great example would be like a power converter. So if you have a switching converter, those can emit a lot of radiation. If that radiation couples magnetically into these components, it would then also induce common mode noise, something like this that you would expect to see here. And so that can then also be canceled by the receiver. And so that's the main advantage of differential pairs, is noise elimination, and then being able to overcome any changes in that ground potential. So the last thing that I want to do is look at a case where you have two PCBs and they're separated by some distance, and maybe they're connected to different power supplies, and you need to route a signal between them. So maybe I've got a component here, I've got a component here. This is going to be a case where we're really going to see the advantage of differential pairs, and this is one of the original reasons that they've been used on long interconnects. So let's say I have a signal here. It's being routed over a cable. Now, if I route this with differential pairs, what's going to happen is if I have a ground plane here and I have a ground plane here, the differential pair is going to carry a signal that, once it's read out, isn't going to depend on the potential difference between these two ground planes. When you supply power to these different PCBs, this ground here may not be at the same ground as this here. So if I were to measure the potential between these two grounds, this might not be 0 volts. It might be something greater than 0 volts or less than 0 volts, who knows? But it may not be 0 volts. So these two grounds are not necessarily the same ground. So this is why with differential pairs, once it's received at the other side, it doesn't care what the ground potential is here. And so you remember, if you look back in the previous illustration where I was writing out the readout voltage that you would measure from these two pairs, what you see is that the ground term, let's call this GND1, and let's call this GND2, neither of these terms are going to appear in the equation for the voltage that you measure at the end of the pair. So these grounds don't really matter. And that's what's really important here, is that by measuring the signals between the two pairs, you wouldn't care if there is some ground offset over this link. So let's just look at a quick example of what would happen if I take a little bit of a practical situation and I have my boards referenced to two different grounds. So let's just suppose for a moment that the potential difference between these two grounds is negative a half a volt. Okay, so basically this ground is a half a volt lower than this ground. So what that means is, let's say I source in a potential of 1 volt on my top pair and then negative 1 volt on my other pair. So once these signals reach over to here, what you would have is you'd have a potential difference between these two of 2 volts between them. But now because of the ground offset, the individual voltages are actually different. So here I was at negative 1 volt with respect to this ground. So then I'd be at negative 0.5 volts. And then here I would be at 1.5 volts. So here I was at 1 volt with respect to this ground. This ground is a half a volt lower. So the total potential difference is now 1.5 volts. So even in this case where each of the individual signals has a different voltage measured with respect to this ground on this PCB, the voltage between them has been maintained at 2 volts. And so that's what's really key here, is it's the difference between these two voltages that's being used to communicate a digital signal across this link. And that's why you have a great advantage with differential pairs, because this ground offset doesn't even matter. What we're looking at here is a PCB layout with some differential pair routing, and you can usually tell that it's differential pair routing because if somebody named the nets correctly, what they did is, if you zoom into the net names, you'll see that they have an underscore N and underscore P here. So this is your cue that this is a differential pair. This side carries the positive voltage, this side carries the negative voltage. And the way that they're routed is they're routed very closely together, the spacing is maintained, and then the width is maintained throughout the length of the route. So I'm just going to kind of zoom out here and show you something that happens near the beginning side of the route. And so what you'll see here with differential pairs is you'll have these little areas here where it kind of juts out like this. And what this is a length matching structure. And so the idea here is that you have to maintain the length of these two traces in the differential pair to be the same throughout the entire length of the route. So the total length of this side, the positive side, is equal to, or very closely equal to, the length of the negative side of the differential pair. And so by doing that, you can ensure that the signals are read out properly. So we're going to do another video that explains why you actually need to maintain this and some of the different ways or different styles that you can use to enforce this type of section here. Okay, everybody, so hopefully this gives you a good introduction to differential pairs. What we're going to do in the next video is we're going to explain a bit more why you need to match the lengths of your differential pairs and what that actually means for reading out a signal and ensuring that the signal is read out correctly at the end of a link. So if you haven't done it yet, like this video, give us a subscription, and be sure to leave your comments and questions. We love getting your comments and questions. In fact, we've been getting so many of them that it's hard to keep up with all of them. So I'm really happy about it, and I will try to get to your questions as they come up. Thanks for watching, everybody, and don't forget to call your fabricator.